Remember early 2020? That feeling the world just, well, stopped, didn't it? This invisible enemy was taking hold, and there was so much uncertainty, a sense that things were unfolding faster than anyone could keep up.
Oh, absolutely. It
Yeah.
truly felt unprecedented, didn't it?
Yeah.
A global health crisis erupting in real time,
Hmm.
really challenging every single system we had in place.
Exactly. And while the world was grappling with that, kind of standing still in many ways, your sources reveal something really fascinating. An unseen sentinel was already at work, not reacting, but anticipating. And this
Mhm.
wasn't a human. It was, well, a complex tapestry woven from algorithms and just vast amounts of data. Artificial intelligence quietly predicting that a storm was brewing.
That's really the core insight these sources provide, isn't it? The COVID-19 pandemic was such a stark, just devastating reminder of our vulnerability to infectious diseases,
Yeah.
but it also undeniably highlighted this quiet, powerful revolution happening behind the scenes,
Yeah.
the transformative power of AI in public health.
You know, traditionally, our approach to public health felt very reactive, like firefighters, sort of waiting for the alarm to ring before rushing to a blaze. You wait for confirmed cases, hospitalizations, then you respond.
That's a perfect analogy, yeah. And
Hmm.
what AI fundamentally enables is this strategic shift, moving from that reactive stance to a proactive sentinel role.
A sentinel, I like that.
Instead of merely responding once an outbreak is already well underway, these systems offer the capacity for anticipation, for really sophisticated prediction.
And that predictive capability gives us something absolutely critical: time. In a pandemic, time is, well, it's everything, isn't it?
Precisely. Predicting outbreaks before they become widespread, maybe even before they're officially reported through the traditional channels, gives public health officials that absolutely precious lead time.
Right.
And that window, it could be the difference between being caught completely off guard and actually being able to make early interventions, mobilize resources effectively, implement policies that can genuinely slow the spread and mitigate the severity.
It's the difference between trying to contain a small fire and, well, battling a raging, uncontrolled inferno.
Couldn't have put it better myself.
Okay, so that's the mission for this deep dive then. We're going to take the stack of your sources, these articles, the research papers, your own notes, and really unpack what they reveal about how AI, and specifically machine learning techniques, have transformed our ability to anticipate, track, and respond to pandemics.
Yeah, we'll dig into some really compelling real-world examples, try to demystify the underlying technology a bit, without getting lost in impenetrable jargon,
Good.
and examine the profound impact these tools are already having on global health.
And it feels crucial to explore the broader implications too, right? Including the human and ethical dimensions. Because like any powerful technology, its deployment raises some really important questions.
Absolutely essential.
So you can think of this deep dive as your shortcut to understanding how these digital oracles are stepping up to help safeguard global health in this, well, this new era.
These systems are incredibly complex, no doubt. They're drawing on data sources we never previously imagined integrating, but the potential they unlock for proactive health defense is just immense.
Okay. Let's pull back the curtain then on what these sources reveal about the AI that predicted a pandemic.
Hmm.
All right, let's kick off with a specific moment, one that grammatically illustrates this fundamental shift we're talking about, moving from reactive crisis response to proactive foresight. Picture the scene. New Year's Eve, December 31st, 2019.
Right.
Around the world, people are getting ready to celebrate, pop champagne, welcome a new decade with, hope and anticipation. But while all those festivities were being planned, quietly, without any fanfare, a small company up in Canada sent out an alert.
That company was BlueDot, and their AI-powered system detected a cluster of unusual pneumonia cases in Wuhan, China.
Wow.
This was the whisper before the roar, wasn't it? A faint signal in all the global noise that, as we now know with hindsight, would soon escalate into a crisis that affected literally every corner of the planet.
And here's where it gets really interesting and, frankly, quite striking when you look at the timeline presented in the sources. That alert from Blue Dot went out on December 31st, 2019. It warned their clients about this cluster, its potential significance.
And importantly, noting that the infection seemed likely to spread via air travel.
Right. Now, let's contrast that with the official announcements from the major global health bodies. The World Health Organization, the WHO, they issued their first public alert about these cases, essentially acknowledging the situation publicly on January 9th, 2020.
January 9th.
And the US CDC, the Centers for Disease Control and Prevention, they made their official announcement on January 6th, 2020.
The significance of that lead time, I mean, it just cannot be overstated.
Yep.
BlueDot provided a heads up 5 full days before the WHO and 6 days before the US CDC.
5 and 6 days.
In the early days of a rapidly spreading pathogen, days, even hours, can be absolutely critical. And this wasn't, some lucky guess based on a single news report. The sources make it clear this was the result of years of dedicated work building a sophisticated AI-driven global surveillance system, one designed specifically to spot these kinds of early signals.
So how is BlueDot doing this? What exactly is their system? Your sources describe it as an always-on global disease surveillance and intelligence system. What's happening under the hood to achieve this? It monitors, what, over 190 different infectious diseases?
That's right, over 190. But the key differentiator, as you highlighted, is that it doesn't solely rely on those traditional official government reports.
Ah.
And that's absolutely crucial for getting ahead of the curve.
Huh.
Official reports, while foundational, can often be delayed. There's bureaucracy, verification processes, or sometimes maybe even political reluctance to share potentially disruptive information quickly.
Right, the information flow can be slow.
Exactly. So BlueDot's system leverages proprietary machine learning algorithms specifically designed to sift through an immense and incredibly diverse volume of data. It draws from literally hundreds of thousands of global sources simultaneously.
So it's processing what people sometimes call the infodemic, isn't it? That just overwhelming flood of digital information out there where the real signals are buried in all the noise.
Precisely. It's a paradox of the digital age, really. The sheer volume of data circulating globally can be paralyzing and confusing for humans trying to manually track everything.
Impossible, almost.
Almost impossible. But at the same time, it provides this incredibly rich, real-time stream of potential information. AI is uniquely equipped to process this fire hose of data and extract meaningful signals from the noise.
So the future isn't just lab reports, then?
It suggests the future of public health surveillance isn't just about the structured data from hospitals and labs. It's about intelligently processing the entire global digital footprint. That includes potentially less formal information sources, maybe even what you might consider rumor data, social media chatter, or anecdotal reports, things that can serve as those crucial, bleeding-edge early indicators.
Okay, let's dive deeper into that data tapestry then that systems like BlueDot weave together. Your sources detail the types of data they process and, crucially, why each time is so valuable for prediction. It's not just one feed, it's many, isn't it?
Oh, absolutely. It's a multi-layered approach combining traditional information with these novel digital signals. So they start by scanning publicly available text data, things like news articles and health forums.
Okay.
The system scans something like 25,000 news sources in 100 different languages, plus official medical bulletins, online discussions happening on health-related forums.
100 languages. Wow.
Yeah. This is how they can pick up on those very early, often unofficial mentions of unusual health events before they make it into formal reports. Imagine someone posting on, say, a local online forum about several people in their town suddenly having the same strange symptoms. It's the kind of faint signal the system is designed to look for.
So it's literally reading the pulse of online conversations about health globally.
In a sense, yes.
Yeah.
It's using natural language processing, which we can touch on more later, to understand and filter that massive text stream. But of course, they also integrate official health notifications and government data. These reports from organizations like the WHO or national health agencies are essential for context, for validation, and understanding the official picture. But as we've discussed, they aren't relied upon exclusively.
Got it. And then there's a data type that might not immediately come to mind for human diseases. Animal health reports. Why bring that into the mix?
That's because of the fundamental nature of so many emerging infectious diseases. Nearly 3/4, think about that, almost 75% of new or emerging microbes that affect humans actually originate in animals.
Right, zoonotic diseases.
Exactly. So incorporating data like livestock reports, veterinary bulletins, or observations of unusual illnesses in animal populations is absolutely vital for identifying potential zoonotic spillover events, those moments where a pathogen jumps from animals to humans. It's looking at the source, the potential origins, before a human epidemic even begins to take hold.
That makes a lot of sense. You're tracing the disease back to its ecological roots, essentially.
Precisely. And then critically, there's the data that helps predict where a disease might travel next. Human mobility data.
This seems key in our connected world.
It is critically important. BlueDot and similar systems integrate datasets like real-time and historical global flight schedules from thousands of airports. By knowing where people are traveling from and where they're going, the system can build these dynamic models to predict where a virus is most likely to be carried next. This capability is essential for enabling proactive risk assessment and allowing target locations to prepare before imported cases arrive. It's connecting the dots on a global transportation network.
It's mapping the pathways of potential spread based purely on how interconnected we all are.
Exactly. And then there's a lesser known, but equally valuable data source, remote sensing data.
Yeah.
This involves using things like satellite imagery and integrating climatic data, temperature, humidity, precipitation.
Satellites, how does that help track disease?
Well, environmental conditions are absolutely critical for many disease vectors. For example, satellite data showing heavy rainfall can help predict conditions favorable for mosquito breeding.
Ah, okay, like for Zika or dengue.
Precisely,
Mm.
which directly impacts the risk of outbreaks of diseases like dengue, Zika, or malaria, or changes in land use visible from space might even signal increased contact points between humans and wildlife, raising the risk of zoonotic spillover.
So the environment itself, the climate, the land use, it can signal where a disease is likely to emerge or spread.
It provides the ecological context and identifies risk factors. And the sheer volume and variety of this data, you've got news, official health reports, animal data, flight paths, satellite imagery. It just highlights why this isn't something human analysts alone can process effectively.
Too much, too fast.
Exactly. This is where AI truly acts as that sophisticated filter. It uses automated workflows and complex algorithms to sift through everything, identify the relevant signals, and extract credible information from all that unstructured text and those diverse data formats.
And it's not just raw data dumping into a system, right? Your sources explain this processed data goes into a data warehouse, then the AI analyzes it, and that intelligence is synced with products for human experts to review. So it's not just the AI making unilateral decisions.
Absolutely not. That human-AI interface is essential. The AI identifies potential signals and synthesizes the data at a scale and speed impossible for humans. But it's the human experts, the epidemiologists, the public health professionals who provide that crucial layer of assessment.
The reality check.
Exactly. They evaluate the credibility, they contextualize the information, and they determine the significance of the signals before any alerts are issued or recommendations are made. The AI is a powerful tool for foresight, but human judgment is absolutely key for translating that foresight into action.
And the value of that time gained, as you emphasize right up front, is just immeasurable. Your sources highlight the rapid warning BlueDot issued within 2 hours of detecting those initial Wuhan cases. 2 hours.
And that alert went directly to their clients, public health agencies in 12 countries, major airlines, frontline hospitals. That incredibly early signal gave those organizations, the ones equipped and willing to listen, precious extra time to initiate preparedness measures, maybe screen travelers, or simply heighten their vigilance.
And you mentioned specific examples of governments or agencies actually acting on this early signal.
Yes, the sources point to instances like the Public Health Agency of Canada, PHAC. They use BlueDot's platform for modeling and monitoring the early spread of COVID-19, which directly informed their strategic decision-making. And in California, state officials reportedly enlisted BlueDot's assistance. They leveraged their mapping technologies and, notably, analysis of anonymous cell phone data.
Ah, the mobility data again.
Right, to predict which hospitals were most likely to be impacted by the incoming waves of cases, and also to monitor population movement patterns to assess adherence to social distancing guidance.
So what does this all mean when you look at the Blue Dot case and the actions taken? It's not just a cool tech story, is it? It shows a clear causal link. AI provides the early signal, and that signal, when acted upon by governments and health organizations, provides absolutely precious time. Time for interventions, for allocating limited resources effectively, for simply being prepared instead of being blindsided.
It's all about translating predictive intelligence into actionable public health policy and strategy. The saving lives aspect isn't solely the AI detecting something. It's that crucial interplay between the AI's capability to identify the threat early and the human institution's willingness and capacity to act swiftly and strategically based on that intelligence. It underscores that critical human-AI interface and the necessity for frameworks that can translate complex predictive data into practical public health decisions.
And Blue Dot's success wasn't just a one-off with COVID-19, was it? They have a history of this kind of early detection, according to your sources.
They absolutely do. They accurately predicted the global spread patterns of Ebola during the massive 2014 outbreak.
I remember that.
In 2016, they accurately forecasted a local Zika outbreak in Florida roughly 6 months before it officially occurred.
6 months.
6 months early. And more recently, in 2023, they alerted clients to the Marburg virus outbreak in Equatorial Guinea very early on.
Your sources mention a table, I think it's table 1, detailing their performance across various outbreaks, and it noted their system detected these events an average of 43 days before official announcements.
That's right. An average lead time of 43 days across a range of different infectious diseases.
Mm.
That demonstrates a consistent, significant advantage. In the race against a rapidly spreading pathogen, gaining over a month's lead time, well, it's an incredibly powerful testament to the potential AI offers in shifting us towards truly proactive preparedness. It gives decision makers room to breathe and, crucially, to act.
Okay, so we've seen the powerful impact of AI in a real-world scenario like BlueDot, demonstrating this shift towards early warning. Now let's peel back the curtain a bit more. How does the AI actually do this? It's not magic, obviously. It's not a crystal ball.
Yeah.
As you put it earlier, it's a highly sophisticated pattern recognition engine. But what does that actually involve, under the hood?
Right. So at its fundamental level, these systems leverage what's called predictive analytics. This is basically the process of analyzing historical data, combining it with real-time streams of information to identify patterns and trends that can forecast future events. In public health, this means anticipating where and when outbreaks might occur, identifying populations most at risk, and understanding how a disease might spread.
So kind of like a weather forecast, but for disease dynamics, using way more inputs, I imagine.
That's actually a really good way to think about it. Just as meteorologists use vast amounts of historical weather data, current conditions, atmospheric models, satellite imagery, all that stuff, to forecast tomorrow's storm.
Right.
These AI systems use past and present disease patterns, mobility data, environmental factors, social signals, and much, much more to forecast the trajectory of potential health threats.
And your sources mention deep learning as a key component here. What is that in simple terms, and how does it help predict diseases specifically?
Okay, so deep learning is a powerful subset of machine learning. You can think of it like building incredibly complex, multi-layered networks, almost like layers upon layers of filters. These networks can learn to recognize extremely intricate patterns hidden within massive amounts of data. Patterns that would be invisible or just too complex for simpler algorithms or even human analysis alone.
Okay, multi-layered filters finding hidden patterns.
Exactly. And when you apply this to disease prediction, specific types of deep learning techniques are particularly useful.
Like looking at patterns over time, you mentioned that earlier.
Precisely. One major area involves analyzing data that changes continuously over time, what we call time series data. This could be, say, daily reports of flu-like symptoms showing up on clinics, or a constant stream of data from environmental sensors, or even aggregated, anonymized physiological data from wearable devices, which we'll get to.
Right.
Deep learning models are trained to look at these sequences of data over time and learn to identify the subtle shifts, the early deviations from the norm, that reliably precede a significant event, like an outbreak.
So instead of just seeing a sudden spike in cases, the AI might see the gradual, subtle changes leading up to that spike.
That's exactly it. It's like a doctor monitoring a patient's vital signs continuously over hours or days and noticing those faint early indicators. Maybe a slight change in heart rate variability, a subtle shift in breathing patterns that predict a serious health event before it becomes obvious. These models learn to spot those faint early symptoms in the data stream of a population's health signals or environmental conditions.
That's fascinating. And what about how diseases actually spread? Through communities across the globe.
Right, that requires a different kind of analysis.
Yeah.
That's often handled by models that are good at understanding relationships and connections. Sometimes they're called graph neural networks, or GNNs. But let's focus on what they do.
Okay.
Diseases don't spread randomly, do they? They propagate through networks. Human contact networks, transportation networks like flights and train travel, even animal migration paths. These AI models are designed specifically to understand and analyze data structured like a network nodes connected by edges.
So they can literally map out that intricate web of connections between cities, people, animals.
Yes, exactly. They can model how an infection might travel along these complex structures. By integrating data about human movement or even social connections, if that data is available and ethical to use, they can predict how quickly a virus might spread through a city or across countries.
Mm.
And importantly, they can identify key nodes or connections that are most critical for intervention strategies.
Like identifying the key airports for screening.
Precisely. Think of it like mapping the global flight network and identifying which hubs are most vulnerable to receiving an infected traveler first,
Mm.
allowing for targeted screening or preparedness measures right there.
That paints a really clear picture of how they follow the pathways.
Hmm.
Okay, and we talked about systems like BlueDot, reading news, and forums. How does the AI handle all that text? That seems like a huge challenge.
It is, and that's where natural language processing, or NLP, plays such a vital role.
Yeah.
This is the branch of AI that enables computers to effectively read, understand, and process human language.
Right.
It's what allows these systems to scan millions of news articles, social media posts, health forum discussions, even potentially anonymized text from electronic health records across multiple languages.
So it's basically teaching the computer to be a global reader and understand what people are saying about their health or what's being reported in any language.
Pretty much, yeah. NLP allows the AI to automatically identify mentions of specific symptoms. Think sudden loss of smell, unusual fatigue, or self-reported illnesses, public concerns related to health events, and extract critical, structured information from that raw, unstructured text far faster and more comprehensively than any team of human analysts ever could.
It's like having a multilingual, hyper-attentive assistant.
That's a great way to put it. An assistant that can read every relevant newspaper, medical bulletin, online forum, and social media feed in the world simultaneously, pulling out and flagging anything unusual related to health.
The scale is just incredible. What other tools are in this AI toolkit for prediction? It can't just be deep learning and NLP, can it?
No, the toolkit is quite diverse. There's supervised learning, which is perhaps the most common type of machine learning you hear about. Here, algorithms are trained on a large data sets where the outcome is already known.
Like past outbreaks?
Exactly. Historical data from past outbreaks versus periods without outbreaks. By analyzing these labeled examples, the algorithms learn the patterns that differentiate situations that led to an outbreak from those that didn't. This allows them to predict the likelihood of a future event when they're presented with new, current data.
So learning from history to predict the future makes sense.
Exactly. Then there's unsupervised learning. This is used when you want to find patterns in data where the outcome isn't pre-labeled. Techniques like clustering, for example, can group regions or populations with similar epidemiological characteristics or risk factors, even if those groupings weren't obvious beforehand.
So it finds connections we might not have seen.
It can, yeah. This helps public health officials target high-risk areas more effectively. Or there's anomaly detection, which is specifically designed to flag unusual spikes or patterns in data that deviate significantly from the norm. This could indicate an outbreak is starting, even if it doesn't fit a previously known pattern.
So it spots something that just looks off compared to how things usually are.
Right. Just, this doesn't look right.
Yeah.
And increasingly, we're seeing the use of hybrid models. These are interesting because they combine the data-driven predictive power of AI techniques with traditional, well-established epidemiological models.
Like the mathematical models epidemiologists have used for years.
Exactly, like the classic SIR models used to describe how diseases spread through a population. Combining AI's ability to find subtle patterns in complex, real-world data with our existing biological and epidemiological understanding can create more robust and, importantly, more interpretable predictions.
So getting the best of both worlds, the power of AI with the foundational understanding of disease spread.
Indeed. And finally, there's growing interest in reinforcement learning, RL. This is a type of AI where algorithms learn by trial and error, essentially. They make decisions to achieve a goal in a given environment and receive rewards for desired outcomes.
How does that apply to pandemics?
Well, in this context, RL algorithms can be used to simulate different intervention scenarios. What if we prioritize vaccinating this age group first? What if we implement a specific type of movement restriction in this particular region? The algorithm learns which strategies are most effective by evaluating their outcomes within that simulated environment.
So it's like testing out different public health strategies in a digital sandbox before implementing them in the real world, finding the optimal path.
Exactly. It allows for exploring the potential consequences of different decisions in a safe, simulated space. All these techniques, though, whether analyzing time trends, Modeling networks, processing language, learning from history, finding anomalies, combining models, or simulating interventions fundamentally rely on the ability to access, process, and integrate those vast amounts of diverse data that we talked about earlier.
Which brings us right back to that core concept. The power of AI here truly comes from weaving together this incredibly vast and diverse data tapestry. Let's look closer at the threads that make up that tapestry. We can build on what we discussed with BlueDot, but look more broadly now at the kinds of information these AI systems are leveraging.
Right. The sources outline several key categories of data, and each provides unique insights. First, there's the bedrock, right? The data public health has relied on for decades. Traditional surveillance data.
The official stuff.
Exactly. Lab reports confirming specific infections, clinical case notifications from doctors reporting diagnoses, and syndromic surveillance, which involves monitoring nonspecific health indicators, like emergency department visits, or reports of general symptom trends, like surges in people complaining of fever or cough.
So that's the formal pipeline of health information.
Correct. But the revolution, as we've said, truly comes with integrating the wealth of information from our digital footprints. These provide those real-time, often unofficial signals that capture activity happening before it necessarily enters the formal health system.
Like what we're all talking about online.
Precisely. Social media activity and internet search trends. AI systems monitor discussions on platforms like Twitter, Facebook, local forums, and they analyze search patterns on engines like Google. They're looking for mentions of specific symptoms. Remember, sudden loss of smell, how that emerged.
Yeah, that was huge.
Or unusual fatigue, self-reported illnesses, spikes in searches for information about specific diseases. This data can capture the very first whispers of people feeling unwell or noticing something strange in their community, often before they visit a doctor or get a formal diagnosis. Remember the Google Flu Trends project years ago?
Vaguely, yeah.
That was an early attempt to use search data as a leading indicator. AI takes this concept much, much further now.
So people are describing their symptoms or looking them up online before they actually show up in the official statistics.
It can be a critical leading indicator, yes. Then there are population mobility patterns. We discussed flight schedules, which are vital for international spread. But during COVID-19, the use of analyzing anonymous cell phone data became particularly relevant and somewhat controversial, too.
Right.
By aggregating anonymized location data from millions of phones, researchers and officials could see broad population movements, predict where people from affected areas might travel next, and even assess how well communities were adhering to public health guidance like social distancing.
That provides this dynamic, almost real-time map of potential transmission pathways, both within and between different areas.
It offers an unprecedented view of how people actually move, which is directly tied to how pathogens spread. And we also have environmental factors. We touched on this, but it includes detailed climatic data, temperature, humidity, precipitation, even wind patterns, and incorporating insights from satellite imagery.
Right, the mosquito breeding example.
Exactly. Forecasting conditions favorable for vectors like mosquitoes after heavy rains can help predict outbreaks of things like West Nile virus or dengue. And satellite data showing changes in forest cover or land use can also signal increased human-animal interaction points, potentially raising the risk of zoonotic spillover events.
So the changing environment itself is broadcasting signals about potential disease risk.
It provides the ecological context that's essential for predicting environmentally linked diseases or understanding the origins of new ones. And then increasingly, we're seeing the integration of individual health data.
Okay, like data from hospitals and doctors' offices.
Yes, primarily electronic health records, EHRs. These contain a wealth of detailed patient information diagnoses, symptoms noted by clinicians, treatment outcomes, lab results. Using NLP and other AI techniques, systems can process anonymized or de-identified EHR data across large populations.
To do what, exactly?
To identify trends in disease progression, maybe understand which patient groups are at higher risk for severe outcomes, spot clusters of unusual symptoms appearing in clinical notes that might not trigger standard alerts, or even evaluate the effectiveness of different treatments in real-world settings outside of clinical trials.
So that's taking all that structured clinical data and allowing AI to find larger, perhaps hidden patterns within it.
Exactly. And then there's a truly fascinating layer, and one that's rapidly developing: wearable technologies. The data coming from our smartwatches and fitness trackers.
Wait, my everyday fitness data could be part of public health surveillance? How does that work?
Absolutely, and it's a really promising area. Data from smartwatches and fitness trackers, things like resting heart rate variability, step counts, sleep patterns, body temperature, even blood oxygen saturation.
The stuff my watch tracks anyway.
Right. This data can serve as incredibly early warning signs of infection, often at an individual level. Before you might even feel sick enough to notice or report symptoms, your body might exhibit subtle physiological changes that are detectable by your wearable device.
Like my resting heart rate just going up slightly, or my sleep being more disrupted, maybe before I feel overtly feverish.
Precisely those kinds of subtle shifts. They can be early indicators that your body is starting to fight something off. And here's the key public health application. When you aggregate that kind of anonymized data from a large number of people in a specific geographic area, you can start to spot patterns at the population level.
Ah, I see.
If you see an unusual spike in average resting heart rates or disturbed sleep patterns across a significant number of people in a particular community, it could be an incredibly early signal that a pathogen is circulating in that community,
Hmm.
potentially days before people start reporting illness or showing up at clinics.
That's incredible. It's transforming personal physiological data into population-level public health intelligence. It really is a vast tapestry, isn't it? Combining traditional reports with the dynamic signals from our digital lives, the environment around us, and even data from our own bodies.
It really is.
Nice.
And it creates this comprehensive, multidimensional intelligence picture that was simply unimaginable even a decade or two ago. This kind of holistic view of potential threats, constantly being updated and analyzed by AI, is fundamentally changing our capacity for proactive health defense.
Okay, so we've explored the incredible capabilities of AI here, providing these crucial early warnings, identifying those subtle whispers before the roar of an epidemic, analyzing this incredibly complex data tapestry. Its emergence in public health has undeniably shifted us towards a much more proactive preparedness model, which, as you say, has tremendous potential for saving lives.
That transformative potential is clear? Absolutely.
Hmm.
And the examples we've discussed really highlight its promise. However, and this is a big however, as with any powerful technology that leverages vast amounts of data and operates with complex algorithms, its implementation comes with inherent responsibilities and significant challenges that demand really careful consideration and navigation.
Yeah, it's definitely not a simple plug-and-play solution, is it? What are some of the critical challenges that your sources highlight, the things we really need to grapple with?
Well, a primary concern, given the reliance on extensive data collection, is definitely data privacy and surveillance risks. These AI systems are most powerful when they have access to huge data sets, right?
Hmm.
And much of that data is inherently sensitive personal health information from EHRs, location data from cell phones, even those intimate physiological signals from wearables.
Right, very personal data.
Extremely personal. Collecting and processing this much sensitive data at scale raises significant privacy concerns. We need robust data protection frameworks, we need strong anonymization techniques, and we absolutely need transparent consent mechanisms. These are all critical to building public trust and preventing potential misuse of this information for surveillance or, frankly, other purposes we haven't even thought of yet.
It feels like a necessary tool for public good, potentially, but one that absolutely requires very clear boundaries, strong security, and public buy-in based on trust that it won't be abused.
Precisely. The public needs to understand how their data, or aggregated data patterns derived from their data, are being used, and they need to trust that it's solely for public health benefit and rigorously protected from unauthorized access or mission creep.
Okay, what else?
Another significant challenge is often termed the black box problem. This refers to the complexity of some advanced AI algorithms, particularly deep learning models. Sometimes, while they produce accurate predictions, the exact steps or the reasoning they followed to arrive at that prediction can be opaque, even to the developers who built them.
So the AI says an outbreak is likely here, but you can't necessarily get a clear step-by-step explanation of why it thinks that.
Exactly. It might point to correlations in the data, but explaining the causal logic can be difficult, and this lack of transparency can be a major barrier in public health. It makes it difficult for human policymakers and health professionals to fully trust and understand the basis of AI-driven decisions,
Especially when those decisions have big impacts.
especially then. Decisions like recommending specific restrictions or allocating scarce resources based on predicted risk. If you can't explain why the AI is giving a certain warning or recommendation, it's much harder to gain public acceptance, or even ensure accountability if something goes wrong. Building trust really requires some level of interpretability, or at least extremely rigorous validation of the outputs.
Yeah, it adds that layer of uncertainty if the why is hidden. People want to understand the reasoning.
They do, and they should. Transparency is crucial for effective human-AI collaboration and public confidence. A third serious risk we have to talk about is algorithmic bias.
Ah, yes, this comes up a lot with AI.
It does, and for good reason. These models learn from the data they're trained on. If those data sets are unrepresentative, if they're incomplete, or if they reflect existing historical biases and inequalities in healthcare access or reporting.
Like data from certain communities being less available or accurate.
Exactly. For example, if data from marginalized communities is less comprehensive or less accurately recorded, the AI models can learn and then perpetuate or even amplify those existing health disparities.
Which could lead to what? Inaccurate predictions for certain populations?
Yeah.
Or maybe unfair allocation of resources, like underestimating risk in one neighborhood while overestimating it in another based on flawed data.
Absolutely. A bias model could potentially direct resources away from communities that are actually at high risk but are poorly represented in the training data. Or it could lead to interventions that are less effective for certain demographic groups because the model wasn't optimized for them. Ensuring data quality, data diversity, and actively working to detect and mitigate bias in both the data and the algorithms themselves are absolutely critical steps. We need to make sure these powerful tools promote rather than hinder health equity.
That's a huge responsibility. And finally, there's the very real challenge of access, isn't there? Not every country or even every region within a country has the capacity for this kind of advanced AI infrastructure and expertise.
That's the significant challenge of unequal access. Implementing and effectively using these advanced AI tools requires substantial investment. You need computing power, robust data infrastructure, technical expertise in AI and data science, and you need the institutional capacity to actually integrate these systems into public health workflows.
And those resources aren't everywhere.
No, they are not uniformly available globally, particularly in low-resource settings that might be incredibly vulnerable to outbreaks in the first place. If we don't actively address this disparity through international collaboration, knowledge sharing, capacity building, equitable deployment strategies, these powerful tools designed to protect global health could ironically end up deepening existing global health inequalities, leaving the most vulnerable populations even more exposed.
So while AI offers this immense leap forward in our ability to predict and respond, realizing its full promise in safeguarding global health, well, globally requires a really concerted effort. It's not just about building the cool tech, it's about navigating these complex ethical considerations, ensuring data quality and representativeness across diverse populations, and crucially, fostering robust human AI collaboration.
That point about human AI collaboration is really the essential takeaway that these sources consistently underscore. The future of pandemic preparedness isn't AI replacing human expertise, it's AI acting as an indispensable partner.
A partner, not a replacement.
Exactly. The AI provides the foresight, it identifies the faint signals and the noise, it synthesizes vast amounts of complex data at speed and scale that humans just can't match. But it's the human public health professionals, the policymakers, the community leaders, the researchers, who must translate that intelligence into confident, strategic, ethical, and coordinated global responses.
The human element, the judgment, the understanding of context, the ethics, the communication is absolutely essential for the AI's intelligence to be effectively and appropriately utilized.
Precisely. It's that combination, powerful AI foresight guided by human expertise and ethical consideration that holds the potential to transform those faint whispers of a threat into effective life-saving action globally.
Okay, so as we wrap up this deep dive, we've seen how AI systems, maybe most famously demonstrated by BlueDot's early warning before COVID-19 became widely known, are fundamentally changing pandemic preparedness. They're providing crucial lead time.
Hmm.
And this capability is powered by sophisticated machine learning techniques like analyzing data patterns over time, modeling how things spread through networks, understanding information hidden in just mountains of text, all drawing on that vast, diverse data tapestry we talked about, woven from traditional reports, real-time digital footprints, environmental signals, and even aggregated data from our personal wearables.
It really marks a significant shift, doesn't it? Moving from waiting to respond to proactively anticipating. It offers the potential for interventions that can mitigate devastating impacts and ultimately save lives.
However, as we've also explored in detail, this transformative power comes with significant responsibilities and challenges. We have to navigate the complex landscape of data privacy and the potential for surveillance risks. We need to address the black box problem, where the AI's reasoning might be opaque. We must actively guard against algorithmic bias that could worsen existing health disparities. And we have to ensure equitable access to these powerful tools across the globe so they don't end up deepening global health inequalities.
AI success in truly safeguarding global health, it really hinges on integrating its remarkable capabilities with human expertise, ensuring its deployment is responsible, ethical, and collaborative, fundamentally grounded in trust and equity.
Which leaves us with a final thought for you, the listener, to consider, building on the themes we've explored from these sources. As we continue to refine these powerful AI sentinels, capable of processing ever more data about the world and indeed about ourselves, how do we ensure the incredible intelligence they provide leads not just to faster warnings, but to truly equitable health outcomes for everyone, everywhere?
Yeah.
What does a future where humans and AI effectively and ethically partner against pandemics truly look like in practice, especially for those communities and individuals who are most vulnerable?
It's a critical question, isn't it? It moves beyond just the technological capability itself and really delves into the societal structures, the ethical frameworks, the global collaborations that are needed to build a truly resilient and equitable global health system for the future we're entering.
And that's where we'll end this deep dive.